Alright, this lesson will focus on the speed of sound. It'll take or make use of concepts we've already talked about up to this point about mechanical waves, so it should be hopefully a little bit of a... Alright, so remember that sound is a mechanical wave. Alright, so a mechanical wave again requires a medium to travel through. And what we've already determined up to this point is that the speed of a mechanical wave is dependent on that medium. Okay, so that's the important thing to remember about sound, is it's still a mechanical wave. Sound still depends on the medium. And the equation we came up with is that the velocity or speed of a mechanical wave is dependent on both the elastic property and the inertial property. Now when talking about mechanical waves such as like a transverse wave or a wave through a spring, you know, we looked at the properties of the tension of that spring and something called the linear density. Okay, so those make up kind of the speed of a wave traveling through a spring. Well, how do we talk about this in terms of sound? All right, sound can travel both through, through solids, liquids, gases. It can travel through really any type of medium. All right, so again, it really is going to focus on the property of the medium. Well, the elastic property is going to represent how easily those particles oscillate, how easily they move back and forth. And the inertial property is kind of the same thing. It's kind of inertia is that mass is really going to look at the kind of the density of that object and how that would affect the speed. All right, so it's kind of these same properties that are going to affect the speed of sound. So remember that sound is a mechanical wave, and all mechanical waves depend on the medium. And really, any mechanical wave can travel through one of three different types of media, which is solids, liquids, or gases. So which one does sound or any mechanical wave travel fastest through? Well, the answer to this is solids. And if you think about the type of medium, why that is, let's look at solids. Well, solids, if you look down at the very microscopic level, you have particles that are very tightly bound, right? They're very close together. So sound, any mechanical wave, is created by some disturbance, right? I'll show a disturbance here by the arrow. And what that disturbance is going to do is it's going to cause the particles of that solid to vibrate back and forth across equilibrium. And remember, sound waves are longitudinal waves, so they're going to vibrate back and forth in the same direction in which the wave is moving. Okay, so the wave is going to move to the right here, they're going to vibrate to the right and to the left. When this particle vibrates, because it's tightly bound, it's immediately going to disturb the particle next to it, and that disturbance is going to move through that solid rather quickly. If you think then of a liquid, the particles are a little bit more spread out, right? Because as you increase the temperature, the particles get more excited, they're beginning to move a little bit more. So that same disturbance will cause the molecule to vibrate back and forth. However, it's going to require more time for that disturbance to reach the particle next to it, all right? And because of that, it's actually going to decrease the speed. The disturbance is going to travel through the liquid a little bit slower than it would a solid. And then take that related to gases. Gases are even more spread out. Same sort of thing is going to happen. That disturbance is going to take more time to travel from one particle to the next. So because of the density of the particles of that solid, liquid, or gas, that's really going to determine the speed at which it travels through. So it's going to travel fastest through solids. So kind of down here is in a table, a list of different values. So you can go from aluminum to copper, those being solids, aluminum having a speed of 6,320 meters per second, and air at 40 degrees Celsius having a speed of 355 meters per second. Notice here, as you go from the solid to a liquid, the speed is decreasing. However, now all of a sudden you get to a gas. And here's kind of the interesting part that we'll focus on, is that the speed of sound in a gas, as you change the temperature of that gas, notice from 20 to 40, the speed is actually increasing. Okay, so that's kind of an interesting fact that we're going to look at. So really, speed, the sound, really one medium through which it travels through that we primarily will focus on is air, right? Obviously, we live in air, we don't live in water, so it's more realistic to talk about the speed of sound in air. All right, so what we saw from that last table is that as you increase the temperature of air, as you saw that it went from 20 degrees Celsius to 40 degrees Celsius, you saw that the speed increased, which is kind of an interesting fact, because if you think about it, as the temperature is increasing, the particles are actually getting a little more spread out than what they would before. All right. So why, when increasing the temperature, would that affect the speed of sound? Why do we get this increase in temperature? All right. And if you really think about it, as you're increasing the temperature, basically you're adding the energy. You're adding more energy into the air. All right. So increasing temperature, adding energy. Well, yeah, the particles are going to spread out, but at the same time, the particles are going to get more excited. So you're increasing the excitement, I guess, of the gas particles. Meaning, yes, they're spread out farther. Because they're more excited, they're going to move around a lot faster, a lot randomly, and the collisions that could occur between these particles are going to happen more frequently. So because of the increase in temperature, because that causes a change in the energy of the gas, that excitedness is going to create more collisions that occur more often. So as you see, as increase the temperature, what's going to happen is that it's actually going to increase the speed of sound. Now we're primarily looking at air. The same is going to apply for all gases, but the following equations we're going to go through is specifically looking at air. So the lab you did in class with the tubes and looking at the speed of sound in air, we were simply looking at the speed of sound at a single temperature. If we were actually to look at the speed of sound in different temperatures, we would come up with this relationship here, which, looking at it, you really get an equation that's of the form y equals mx plus b. So it's an equation of a direct relationship, where our y variable, our dependent variable, is the velocity, and our independent variable is temperature. So it's showing that the velocity is directly related to the temperature of the air. Now this, again, specifically is talking about air. And even though sound will travel faster in a solid, it'll go slower in a liquid, when it gets into a gas, actually, because of the changing temperature, it'll actually start to increase speed as the temperature of the gas changes. And this equation specifically, again, looks at air. And what it says then is that as the temperature of air increases, the speed of sound through air is actually going to change. So looking at some of these values, is that if you think the temperature is 0 degrees Celsius, if you look at the equation, this second term would drop out and you're left with 331 meters per second. So that's the temperature at 0 degrees Celsius. Kind of one of the common temperatures you'll see used in the textbook, and the value might be slightly different, but at 20 degrees Celsius, which is about room temperature, if you plug it into the equation, you get something around 343 meters per second. And usually when dealing with problems, this will be the temperature that they give you. But notice again, as we're jumping from 0 to 20, the speed is increasing here by about 12 meters per second. So the speed is increasing as the temperature increases. Which again is an interesting fact. As we said, it goes in order from fastest to slowest, solids to liquids to gases. So this is kind of, as it gets to a gas, it's kind of counterintuitive of what we're seeing. So kind of the equations we have, this equation simply looks at velocity in terms of degrees Celsius. Okay, we can also relate it to Kelvin. And this equation down here is really saying the same thing, but now it's talking about velocity in terms of Kelvin. Right, so really the same thing. This 331 again is the temperature, 0 degrees Celsius or 273 Kelvin. Really 200, if you look here, 273 Kelvin divided by 273 will give you 1 times 331. That'll get you that velocity at 0 degrees Celsius or 273 Kelvin. So let's do a simple example of calculating the speed of sound in air depending on the temperature. So if you want to follow along, we will be looking at Chapter 14, number 3. Okay, so in this problem, if you want to open your book and follow along, it says that the coldest recorded temperature of air on Earth, negative 128.6 degrees Fahrenheit, occurred on July 21st, 1983 at Vostok, a Russian station in Antarctica. So we want to know, what is the speed of sound in air at this temperature? So the temperature that we have is equal to negative 128.6 degrees Fahrenheit. And we want to know, what is the speed of sound at that temperature? So looking at the equations we just derived, the speed of sound in air is equal to 331 meters per second plus 0.6 times temperature in degrees Celsius. We also have the other equation with Kelvin, but I'm going to focus on this one. So the first thing we need to do, looking at this equation, in order to determine V, we need to first get the temperature in degrees Celsius. Temperature we're given is in degrees Fahrenheit, so it's a simple conversion. Temperature in degrees Celsius is going to equal 5/9 times your temperature in degrees Fahrenheit minus 32. Okay, so plugging in what we know, it's 5/9 times negative 128.6 degrees Fahrenheit minus 32. And this will give us our temperature in degrees Celsius, which if you do the math, you get negative 89.2 degrees Celsius. Now, simple plug and chug, plug it into the equation. So our speed is equal to 331 meters per second plus 0.6 times negative 89.2 degrees Celsius. Again, here the negative sign matters, and if you go ahead and calculate that, you get a velocity of 272 meters per second. So notice at 0 degrees Celsius we would get a speed of 331, and at negative 89 degrees Celsius we are getting a speed of 272. Okay, and that should hopefully make sense to you. We said that as you increase temperature, that would increase the speed. So if we're decreasing temperature, that would decrease the speed of sound. So sound would actually travel slower in air at that temperature.